Hello viewers, you are welcome once again to this program, a series of programs on mathematics. We started with the programs on matrices and determinants. This is the third program in this sub-series. Last time, remember, we introduced you to the operations on matrices, and in that program we did talk about addition of matrices. After talking about the addition of matrices, their properties and how to function with that, we went on to the introduction of multiplication in matrices. And in this program, this is exactly where we pick up our threads, and we once again go to the situation where we are talking about the multiplication in matrices. Let us consider this situation where two friends, Rekha and Suman, they go out to the market to purchase certain notebooks and pencils. Rekha wants to buy 10 notebooks and 12 pencils. Suman decides to buy 15 notebooks and 10 pencils, and the cost of one notebook is 12 rupees and that of one pencil is 2 rupees. We are interested in knowing exactly how much it is going to cost each one of them. So, we are interested in working out how much amount is to be paid by Rekha and Suman. So, we write this information for the two friends like this. Remember, this was 10 notebooks, 12 pencils, 15 notebooks, 10 pencils, cost of one notebook and cost of one pencil, and we want to find out the total cost. So, for that we do this exercise of multiplying 10 times 12, 12 times 2, this is the cost coming out in respect of Rekha, 15 times 12, 10 times 2. See how we have gone about the multiplication. What we did was we multiplied this numbers respectively with these numbers with these numbers, and that is how we got these two informations. And so, Rekha has to pay 144 rupees and Suman has to pay 200 rupees. But is it not the common nature that whenever we are buying the material, we do not just go to one shop and buy it? Most of the time we try to compare the cost. This is what these two friends also did. So, Rekha and Suman went to not one store, to another store too, and let us see what is the comparative cost now. At store 1, these are the two costs: notebook 12 rupees, pencil 2 rupees. Store 2, 11 rupees is the notebook and pencil is 3 rupees. In the matrices, use of matrices, we write down this information in this form. While writing this form, we say 10, 12, 15, 10. Remember, these are the notebooks, these are the pencils, and this is the cost of one store: pencils here and the notebooks here, pencils and notebooks. To find out the cost, we exactly go the previous way. We multiply these two items with this. So, 10 times 12, 12 times 2, this is the information that comes here for store 1, and then 10 times 10 and 12, 11 and 3. So, 10 times 11, 12 times 3, this is the information in respect of second store, the cost that the person has to pay, Rekha has to pay for store 2, and 15 times 12, 10 times 2, again we are going the same way, that is picking up the row from here and the column from here, information reflected here. This second row, this second column gives us the information here. So, when we compile this information, we find that we will be able to find out the comparative cost of the two stores, and this is what exactly happens. When you multiply, remember last time you got 144 and 200, this time you are getting 146 and 195. This is the cost that in the store 1 Rekha has to pay, in the second store she pays 2 rupees extra, Suman saves 5 rupees here. So, it is up to them to decide exactly what is to be done. Let us take these two matrices once again. Remember, the process of multiplication went like this, that first element we got by this multiplication, and the element second one we got when we multiplied these two with this, and then we multiplied these two elements with these, and the second information was when they were multiplied by this. That is the element from row 1 multiplied with the elements of column 1 of the second matrix, row 1, column 2, row 2, column 1. This is what comes at this stage, and then row 2, C 2. Does it not tell you exactly how to decide as to how to carry on the multiplication in matrices? The resultant matrix, let us have another look at this. The resultant matrix, the first element, this one is in row 1 and column 1, will be obtained by multiplying the elements of row 1 of the first matrix with the elements of the column 1 of the second matrix. This element will be obtained by multiplying, because this is in row 2 and column 1. So, row 2 of the first matrix, column 1 of the second matrix, exactly in for these row 1 of the first matrix and column 2 of the second matrix, R 2 R C 2 in the like manner. Let us have another situation and try to see what happens when we are multiplying these matrices. There is one row, 2, 3, 4, and now we want to multiply this with this matrix. Follow the same process, multiply these with these, this comes as the first element. So, 3 times 6 2 is 6, and then plus 4 times 5 is 20, 5 times 1 is 5, this comes as our first element. Now, we want to multiply this with this to get the element here. 3 times 4 is 12, 4 times 6 is 24, 5 times 0 is 0. Now, the second row will come here, 2 times 2 is 4, 3 times 5 is 15, 4 times 1 is 4. To get this element, this is second row second column. So, second row second column, 2 times 4 is 8, 3 times 6 is 18, and this is 0. This will be the matrix that we will be getting after multiplying these two. Now, before we go on to finding certain very meaningful trigonometry cases in the multiplication of the matrices, meaningful because not all the pairs of matrices can be multiplied together. Now, before we go to that, let us take another situation. We have this situation here, a matrix A 4 2 1 2, the matrix 2 1. We can multiply this. Surely recall the store where the two friends had gone to buy the things. These were the items, the cost, and surely you can multiply. When we come to this particular situation, what happens? If I want to multiply this, remember I have to go from row to the first column. 3 can multiply with 2, 1 can multiply with 1, but where will this 2 multiply? Surely we cannot. When we cannot multiply, similar will be the case for this one. So, these two matrices cannot be multiplied together. What of this third one that we have written down here? A, B, C, A multiplies with C, A C, and then B multiplies with D, B D, C multiplies with E, C E. and the result of multiplication is available. This shows that we have got to very clearly define as to the order of the matrices before we can start multiplying. But before we start with the order, there is another interesting situation that I want you to see. Can you multiply these two matrices? Intuitively you can say, recalling the case of two stores when 2 items each, 2 costs each were given, similar situation. Now, in case I try to multiply this, 1 times minus 1 is minus 1, 1 times 1 is 1. So, that means I go from here and multiply like this. Then this element, first row second column, first row second column. So, it is 1 and then minus 1, because 1 times minus 1, this is minus second row here, and first column minus 1 plus 1, and 1 times 1 is 1, 1 times minus 1 is minus 1. What do you get? Don't you get here, this is 0, this is 0, this is 0, this is 0. The matrix that we are getting is 0 0 0 0. Remember what you called this matrix? Yes, in addition this was the identity matrix or the 0 matrix. So, the 0 matrix we are getting even when the two matrices that we are multiplying, they are not each equal to 0. This is not 0, this is not 0, and still the product that is coming out to be is 0. Look at another situation, 0 0 5 6 3 0 4 0. This is not a 0 matrix, this is not a 0 matrix. Let us try to multiply. Remember, first row first column gives us the element here. So, 0 times 0 3 is 0, 5 times 0 is 0, then this is first row second column. So, first row second column 0 plus 0, then what of this, second row first column, second row first column here 0 0, then again here 0 0. You are once again getting a 0 matrix, an identity matrix in addition this is called. So, in multiplication, in numbers it may not be happening, it does not happen. When we multiply two numbers, we get answer 0 only when one of the two numbers is 0, but in case of matrices, even when neither of the two matrices is 0, the result of multiplication surely can be 0. Here is another situation which is an interesting one, where we talk of this matrix. Do you think this matrix is a 0 matrix? Surely no, this is not 0. So, we have got 1 0 0 0, and let us try to find out a square. A square means we have to multiply this matrix with itself. What will be the result of this multiplication? Multiplying this and this is 0, 1 here, this is 0 here, then multiplying this is 0, this is 0, this one multiplying with this, you get this 0, and this is 0, this one with this is 0 and plus 0. The matrix that you are getting is 1 0 and 0 0. Compare this matrix A square with A. A is 1 0 0 0, A square is 1 0 0 0. Isn't that another interesting situation? Have you ever seen in numbers that you square the number and you get the number itself, except in case of 1 and 0. But in this case that we saw this particular case, this is not an identity matrix, that means this is not 1 and 1 here, this is not 0. So, it is again another difference, which is a remarkable difference between the matrices when we are multiplying and the numbers which we are squaring or multiplying. Now, that means we are on to the situation where we have got to talk about the compatibility for multiplication of two matrices. We have indeed intuitively talked about this. Now, let us talk about this in details. This is one matrix I am writing. Can I multiply this matrix with this? Surely I can, because 2 can multiply with A, 1 with 2, and that will be our element for first, and then similarly here this will multiply with the column, this row with this column, and you will be getting the answer. So, these two matrices are compatible as far as multiplication is concerned. What of this? What can you say about these two matrices? 3 4, when I multiply this row, this is this row only with this column, 3 will multiply with 4, what of this 0? Means these two are not compatible. Take yet another example, 3 4 5 2 1 0, we multiply this with 2 5 0 1. It has got again another situation that we have got 3 columns here, 2 rows, 2 columns and 2 rows. When we try to multiply, again the same situation comes, 3 can multiply with 2, 4 can with 0, but what of 5? Not compatible. So, this is leading us on to a situation where we have got to really decide exactly when we can say that the two matrices are compatible for multiplication. For that purpose, we give you a very simple straight rule, that is, in case you write the rows columns of one matrix, second matrix, in case you find that this number is the same, that is the columns in the first matrix match with the number of rows in the second matrix, then the two matrices are compatible for multiplication. Say for example, 3 4 5 2 0 1, one matrix. How many columns here? 1 2 3. So, in order to be having a matrix which is compatible for multiplication with this one, I must have, see the columns are 3, how many rows? Surely 3 columns, 3 rows it must have, 2 4 5 1 0 1. Now, this is a matrix which is 2 by 3, this is a matrix which is 3 by 2, this is 2 by 3 and this is 3 by 2, and you can multiply. Multiplication will be this row multiplied with this will be the first element of the first row, this multiplied with this will be the second element of the first row, that is the second column, similarly from here. Now, what is the result that we get when we actually multiply these two? 3 2 6, 4 5 20, 5 0 0, 3 4s are 12, 4 1s are 4, 5 1s are 5, 2 2s are 4, 0 5s are 0, 1 0 is 0, 2 4s are 8, 0 1 is 0, 1 1 is 1. In other words, the matrix that I am getting is 26 and 16 and 5 21, 4 and this is 9. This was 2 by 3 matrix, this was 3 by 2 matrix. When I multiplied, I get a 2 by 2 matrix. These figures are very significant. This is 2 2. So, whenever you are multiplying the matrices, if it is 2 by 3, 3 by 2, the multiplication will be possible only when these two figures match. If this is 3, this to be 3, if this is 2, this has got to be 2. This is the condition. Second, the answer of multiplication will give us a matrix which will be so many rows and so many columns. In general, we can put down this as, if I have got a matrix m by n and I multiply it with a matrix n by p, then the resultant matrix will have m rows and p columns. This is the general rule: m rows, n columns, n rows, p columns, then the resultant matrix will have m rows and p columns. That reminds me of another very interesting situation. See here, do you think these three matrices are compatible for multiplication? Surely they are. 2 by 2, 2 by 2, 2 by 2. So, I can multiply any two together. In that case, what will be the result for a b when I multiply a with b? I get 1 times 0, this is 0, 0 times 1 is 0. So, my first element is going to be 0. The first row, second column, again I will get 0. 0 0 with this, 0 here, this multiplied will give me a 0 0 matrix. What if I multiply a and c? A and c, first row, first column, again I will get 0, first row, second column, this is 1 0 0 1, again 0, this one multiplied with this 0 0, again 0. I am getting a b and a c both equal. See, when we looked at the original matrices, none of these three was a matrix which was a 0 matrix, and still a b and a c are coming out to be equal. Can I say that a b is equal to a c? Surely they are, because every element matches. Now, a b and a c are equal. Does it not remind you of algebra once again? Whenever you had a product equal and this as common, you would say b is equal to c, but here in this particular case b is not equal to c. See, this is 0, this is 0, this is 1, this is 0, this is 0, this is 0, this is 0, this is 1. So, these two matrices are not equal. Even not being equal, we are multiplying it with a third matrix and we are still arriving at a result which is giving us a matrix which is the product, and the two products a b and a c come out to be equal. Now, after doing this much, we are now ready to go on to the various properties that we want to deal in case of multiplication. Remember, in addition what we did, we started with commutativity and we start with the commutativity here. Okay. Commutativity will mean what? That if I have got a matrix A and a matrix B, then commutativity would mean that this product has got to be matched with this product. Now, these products, in case of addition, when we are adding, we found that that was equal, but is it very much true in case of multiplication? Let us try out a few examples and see. 3 4 1 matrix, 1 0 with this is A, and I write down B. I am taking up a matrix B which is compatible for multiplication. I get 1 2 0 1. These two are compatible. What will be A B? 3 multiplied with 1, 4 multiplied with 0, first element will be 3. 3 multiplied with 2, 6, 4, that is 10. See, 3 2s are 6 plus 4 times 1. 1 times 1, 0 times 0, which is equal to 1. 1 times 2, 0 times 1, so this is 2. Let us see what is B A coming out to be. We will be reversing the process, that row from here column from here. You have got to get into this habit of looking at the right perspective when you are multiplying. So, 1 2 first row with first column, 1 times 3 is 3 and then 2 times 1 is 2. See 1 3 2 1, this gives us 3 and 2 5. Then first row second column 4 and 0. So, this comes out to be 4. Second row 0 3 is 0 1 1 is 1. Second row second column 0 4 is 0 and 1 0 is 0. What can you say about these two now? Do they match? 3 10 5 4 1 2 1 0. It does not come true. See, this is another situation that even when the two matrices are compatible for multiplication, the result may not be commutative, but then there are cases where the matrices may not be compatible for multiplication at all. Say this one. One, two, 3 rows, 3 columns, and in case I have here 2 1 0 0 1 3, is it compatible for multiplication? What should I have? This is a 3 by 3 matrix, this is a 2 by 3, these do not match. So, even multiplication cannot take place, let alone the finding of A B equal to B A or not. This is another case. Yet another case could be that I have got a 2 by 3 matrix, say this one 1 0 1 2 1 1. This is a 2 by 3 matrix and I multiply it with 1 2 0 1 2 1. This is 2 by 3, this is 3 by 2. I am supposed to get a 2 by 2 matrix, and that is what I will get when I multiply these two. Now, in case I reverse the process, say this is 2 by 3, this is 3 by 2. So, these 3 are matching. So, my result is going to be a 2 by 2 matrix. This is what the answer is going to be. But in case I reverse the process, that is I bring it first here. So, I will have a 3 by 2 matrix and on this side a 2 by 3 matrix. I can still multiply because these two are matching, but the answer will be a 3 by 3 matrix. So, no question of their matching. This is another situation. So, when we talk about commutativity in matrices, there are cases where even the multiplication is not possible, there are cases where the multiplication is possible, but still we are not getting the desired result. Let us take another situation where we talk about the identity or the unit matrix. Here this is 2 by 2 and you know this is 1 and 1. So, it is a unit matrix. In case I multiply this with any matrix, what is the result? 1 like this. So, 1 times 4 0. So, first element is 4, this is 3 and this is 0. So, 3, this one 0 and 4, this one 0 1 5 5, I get back the same matrix. And this will be true whether you take a 2 by 2 matrix, 3 by 3 matrix. In case it is a 3 by 3 matrix, the identity element will also be, the identity matrix will also be 3 by 3, only then you can multiply, or in that case you will always be getting, when you are multiplying, the matrix itself as the result. Now, here the property does match with the numbers. Apart from these, when we talk of matrices, we have got to talk about this particular case, that is when multiplication is distributive over addition. This will happen only when multiplication exists, that means the two elements are this B C, we can add them in case they are of the same order, remember from addition, and we can multiply with A only when they are compatible for multiplication. Then this result can be checked by you, and this is the last result we are giving you in case of multiplication. We will be going over to multiplication with transpose matrices in our next program. Till then, see what you have learned. Thank you.